Okay, I think we start now. Welcome everyone. This is the second in our seminar series. So the first talk in the seminar series was a few months ago already by an external speaker. But this is also the first time that we have a speaker internally. So thank you, Inho, for volunteering to present. And I think the presentation is really timely because it comes right just a few days after the publication of your paper in Science Advances. So congratulations on that.
Thank you.
It's a fantastic paper and it's already making a lot of noise on Twitter from what I could see. So congratulations and well done. Really happy to have everyone here. This is all a new experiment. So we're hopefully going to perfect this CHM seminars being online because I really would like this to become a staple to bring us together and to expose us to new ideas, sometimes outside of our focus area. So that's still good. It might help us connect also with other people at the center, but also people at the institute and maybe more broadly. So some of these seminars will be public facing at some point too. So it depends on which stage things are at. So we hope to build like a mailing list for the center so that people interested from within the Berlin area or even outside can also join us. And I think that would be a nice channel for promoting our work, getting feedback and so on. So I'd like to quickly introduce Inho. Obviously, everybody here I think already knows Inho at least, has heard of Inho, but he's joined us recently and he's already been working with me and with Morgan Frank, my former student, as well as our collaborator, Heijin Yoon, who's worked with other people like Manuel as well in the center in the past. And Inho spent some time at Kellogg during his, I think during your PhD, right?
Yes.
Yeah, and has really become part of this complex systems physics applied to urban systems as well as labor. So that's, I think, a very fertile area. So we're all looking forward. So thank you again, Inho. We're all looking forward to hearing about the paper and about the plans. You know, how to the next steps you're thinking about as well. So without further ado, please go ahead.
Yeah. Can I start screen sharing? Okay. Yeah. First,
your slides.
yeah, great. Yeah. First, thank you, Iyad, for the great introduction, and I'm very pleased to present this our new paper at our CHM seminar. And yeah, and I'm Inho Hong, and I'm a postdoc at the CHM. And then today I'm gonna present about our new paper, The Universal Pathway to Innovative Urban Economies, published in Science Advances last Friday. Yeah, so it's just a few days ago. Yeah. So before we start, I'm gonna introduce myself very briefly. So I'm currently a postdoc at CHM. I started this position from this March. And yeah, as Iyad introduced it, my background is physics, especially on the complex systems. And I'm from Korea, and I graduated last year. And I did a very short interim postdoc position in Korea, and then I moved to, I joined CHM. And I also I've been to the Kellogg School of Management and the Northwestern Institute on Complex Systems for 1 year. And my research topics cover the various topics like social mobilization and future of work. And during my PhD, I also worked on the human mobility and the science of science. But I think these topics look very versatile, but I think there is some common point, and this is that it's all thing the complex interactions on some geography. So I think yeah, we can find many interesting future collaboration topics topic from this kind of works. And after I joined the CHM, I'm focusing on the social mobilization and the future of work. And I'm currently working with Manuel and Alex and Leonardo on this project. So yeah, today I'm gonna introduce our new paper, the Universal Pathway to Innovative Urban Economies. Yeah, published in Science of Advances. So before we start, I'm gonna introduce my team. So the Morgan was a student at MIT, and he's now assistant professor at the University of Pittsburgh. And Iyad is our director, and yeah, Iyad is here. And Usong is my PhD advisor in Korea. And Haejin is the corresponding author of this paper, and she is the assistant professor at the Kellogg School of Management at Northwestern University. So let me start from introduction to the urban scaling theory. So the urban scaling theory is about the relation between an urban indicator and the population size, and it describes the relations of this the indicator and the population size as a universal rule across all the cities in a nation. So in this left figure, each flag denotes each individual city in a country. And we can see that a single universal rule for this for all of these cities. And we can see that this urban scale relation shows a single equation of the urban indicator and the population size. And the interesting thing from this relation is that the scaling exponent, the beta, and as you can see, this relation is in the form of the power law, the log function. So this relation is non-linear; it's a non-linear relation. And if this the scaling exponent beta equals to 1, then this relation just becomes linear. So it means that the size of an urban indicator is just proportional to the population size. But interestingly, we can observe some superlinear, which means that this scaling exponent is larger than 1, and or sublinear relation, which means that this scaling exponent is smaller than 1. So in this case, we can observe very interesting relations. So for example, if the population size is doubled, like if we change it from n to 2n, then for a superlinear relation of the beta equals to 1.5, so in this case, the size of the urban indicator y becomes 2.8 times of the original size when the population is doubled. But for the sublinear relation, which is for example, the beta is equals to 0.5. So in this case, when the population is doubled, the size of urban indicator becomes 1.4 times of the original size. So it's depending on the scale, the size of the scaling exponent, the urban scaling relation shows very different relations, by the population size. So so we also we can observe these kind of urban scale relations in the urban economies, and we can observe this kind of urban scale relations for each different industry sector of urban industry, and also we can measure the scaling exponent for each different sector. So this is the example of the scaling exponent for the number of establishment in the urban economies, and we can find that interestingly the size of the scaling exponent varies. For the characteristics of the industries. So, for example, the manual industries like agriculture and mining have sublinear scaling exponent. So, in this case, the scaling exponent is smaller than 1. So it means that this industries are the increase of these industries is less than the population size. And we can also observe some superlinear scale relation in the cognitive industries like management and professional services. So in this case, the scaling exponent is larger than 1. So it means that these industries are more concentrated in the large cities. So interestingly, we can observe that the kind of the characteristics like a manual labor based or cognitive labor based are related to the size of the scaling exponent. So here's some very short explanation on why this kind of characteristics of industries are related to the size of the scaling exponent. So it is believed that this the superlinear scaling is related to the interactions. So in general, the cognitive industries have, I believe, that have more interactions inside these industries and the process of some kind of productions. So yeah, so that's why this kind of cognitive industries have superlinear scaling relations. So yeah, so for example, in general, the size of interactions are more than the population size. So because it's the interaction of between the pairs. So in this case, we can think that this this kind of the interactive features of the cognitive industries make the superlinear scaling relations. So yeah, so motivated by from this scaling relation, we wanted to understand the longitudinal changes of the urban economies. So this is schematic is about the scaling relations, and as we can see, the x and y axis are about the log economic size and the log population. So it's about the general scaling relations. And in this schematic, the red dot means each individual city, and then the dotted line is about the scaling line. So as as urban scaling explains, if the this economic size is related to the population size, so the urban scaling relation perfectly, if the urban scaling relation perfectly explain the longitudinal change, so in that case, the temporal change of the city of interest, like this blue dot, will follow the scaling line. As the scaling relation describes. So in this case, the development of each industry, each city, the trajectory of each industry, each cities will follow this scaling line as the time proceed. So we call it as named it as a recapitulation, and we're gonna test if we can observe this kind of the phenomena in the data set. So this is our motivation. So yeah, from this motivation, we made two research questions. So the first one is to observe the different economic structure by the population side, which is expected from the scaling relation. And the second question is to observe the longitudinal pathway described by the scaling relation. So by doing that, we wanted to show whether the urban economic changes follow the common universal pathway described by the scaling relations. So this is the about the data set. So we in this study we use the U.S. urban employment data set, and it has three dimensions. The first, the time, industry, and city. And the time has a 16-year span from 1998 to 2013. So it has 16 time points. And for the industry classification has very different levels. So at the lowest level, it has like 1,000 industry sectors. But in this study, we mainly use the highest the level of classification, yeah, to for the significance of the scaling relation. So in this case, the sectors there are 18 industry sectors, and the cities are defined as the metropolitan statistical areas, and there are 350 cities in the dataset. So we use the number of employees for these three dimensions. So yeah, let me start from the different economic structure by the population size. So we first to characterize the economic structure by the of the cities of the different population sizes, and then the networks on this in this slide shows these economic structures. And yeah, I will go through the details, and then in this network structure, we measure the importance of industry sector in each city, and we measure this importance by using the liberated comparative advantage. I think many of you are familiar with the definition of this concept, but yeah, the liberated comparative advantage is just the ratio of the proportion of industry sector in a city to its the nationwide proportion. So, for example, if the manufacturing has a 30% of proportion in a city A, and its proportion in the nation is like 20%, then the RSA value becomes 3 divided by 2. So, and then we measure the importance of the industry for the cities of different sizes. And then, yeah, so in the network of, in the network in the left figure, it shows the economic structure of the smaller cities. And in this figure, each node denotes the each industry sector, and then the size means this importance of the industry. So it is sized by the liberated comparative advantage, and then the color means the scaling exponent of that industry sector. So yeah, so we can see that in the smaller cities, the industries, the more the manual industries like agriculture, mining have high liberated comparative advantage. But in the large cities, on the right figure, the industries like the cognitive industries like management and the professional services have high liberated comparative advantages. So it means that large cities are more characterized by the cognitive industries, while the small cities are more characterized by the manual industries. So from this the holistic view, we further characterize this kind of the different economic structure by the population sizes. So this left figure is about the relation of the liberated comparative advantage versus on the population size, and we can see that the manual industries like agriculture and mining have decreasing trend with the population size. So it means that these industries are more characterized in the small cities, and also we can observe that the cognitive industries like management and professional services have increasing trend. So it means that these industries are more characterized in the large cities. And also we can observe the point of transition that these trends cross. So at and this point of transition is at the population of 1.2 million. And we further we confirm this kind of empirical the observations by analytic model. So we derive the analytic model for ICA and the scaling, and this model is about the this model is derived from the definition of the ICA and the scaling theory, and then we this model explains the ICA as a function of the population size and the scaling exponent. And the reason why this analytic model is important is that this, as far as I know, this is the first connection between the ICA and the urban scaling theory. And the ICA has been used mostly in the geography or economic geography, and it is named that in this field is often called as the location quotient. Yeah, and which means the locational importance of some measures. So it's yeah this concept of ICA is mostly more used in the conventional studies in the cities, and as you know, the urban scaling theory is more used in the physics and the computer system. So these two concepts are not well integrated in the previous studies, but yeah, in this study we suggest this analytic model that combines these two concepts. So yeah, I think this analytic model is quite a very meaningful contribution to the academia. And then the other interesting from this observation is that the vertical profile of this in this figure means the economic profile of the industry profile of a city. So if the figure shows that the industry profile of a small city and the large city is completely different. So from this observation, if we measure this correlation between the industry profiles of the cities of different sizes, then we will get the economic clusters of large cities and small cities. So this is the result. So in the right figure, I ordered the cities by their population rank, and the color shows the correlation between a correlation of industry profiles of different cities. So in this figure, we can see two very clear clusters, and one is about the large cities at the left lower side, and the other one is about the small cities on the right upper side. And we can see that from this figure, we can see that scaling divides cities into large city economies, which is characterized by the superlinear and the cognitive industries, and the small city economic cluster characterized by the sublinear and the manual labor-based industries. So far, we have investigated the economic structure by the population sizes, and now we go back to our second question about the longitudinal trajectories explained by the scaling relations. So so here we first start from the trajectories of cities in the scaling plane. So the left figure is about the longitudinal changes in the education industries, and then this figure is also about the scaling relations, because the x-axis is about low population, and the y-axis is about the low employment size. So the line on the figure is the scaling relation in 1998 and 2013. And in this figure, each arrow means denotes the trajectory of each individual city between 1998 and 2013. And if the scaling urban scale relation perfectly explain the longitudinal changes of the cities, then the arrows, the trajectories should follow the scaling line. And we can observe that in the education industries, these kind of trajectories are quite well aligned with this scaling line. But in some industries like manufacturing, on the right figure, we observe very strong trend, like this figure. So in this case, if we try to measure the longitudinal scaling effect, then it becomes like just a very strong negative relation, because when because the employment size of every city decreases during this the 16 years. So to accurately measure this kind of longitudinal scaling effect, we need to decompose the trend from this the trajectory of cities. Yeah. So this is how we did. So the first equation is about the cross-sectional scaling relation. So yeah, it's just the usual the urban scaling relation, and then by taking logarithm and taking time difference on the both side, we can get the second equation about the temporal changes. This one is the kind of linearized form, and then this equation decompose the employment change of a city into the nationwide trend and the city-specific growth term. So in this equation, the first term is about the common trend over all cities in the country, and the second term is about the longitudinal change by the population changes. So that the second term is the longitudinal scaling term we wanted to get, and the right figure, the right schematic further explains this kind of decomposition. So in this example, this blue arrows shows the nationwide trend between two time points, for example, 1998 to 2013. And this black arrow, the black thick arrow is the city of interest. And then on the lower side, we can see that this the black arrow can be decomposed into this nationwide trend and the scaled growth term. And yeah, so because this nationwide trend is common to every city, so we can just measure this the common trend, and we can remove this trend from the black arrow. Then the remaining the changes, this red arrow shows the amount of the scaled growth by the population changes. So here, this beta hat term shows the degree of this longitudinal scaling effect. So this is the result of the detrending this common trend. So the left figure is the original trajectories of cities in our data set. And the second figure on the right is about the trajectories of cities that we detrended the common trend. Yeah. And on the right figure, we can see that the trajectories of cities are more well aligned with the scaling line. So this shows some evidence that the longitudinal employment changes scale with the population changes. And this observation is also the first observation that measures the universal longitudinal patterns. And actually, there was a few attempts within a few years from 2018 to this year, and and a few papers were published in very prestigious journals like PNAS and the Science Advances, but these studies failed to observe this universal longitudinal patterns because these studies didn't decompose and remove this common trend. So yeah, so this kind of detrending is very one of noble contribution of this paper. So from this observation, we further characterize the amount of this longitudinal scaling. So for example, if the longitudinal scale, if the scale relation perfectly explains the longitudinal changes of cities, then the value of the longitudinal scaling exponent should be the same with the cross-sectional scaling exponent. So we define the metric called recapitulation score to compare these two scaling exponents. So this metric is just the similarity of these two metrics, because the second term is about the relative difference of difference between two. So, and then this metric becomes one if these two scaling exponents are the same, and then the metric becomes to 0 when there's no correlation between two scaling exponents. And then we measure this recapitulation score for each different industries, like the right figure. And then we observe relatively high recapitulation score on average, like 0.7 over the industries. And also we can find we can see some variations by the industry sectors. And so in general, it shows that the recapitulation is prevalent in most industries. And we can find another very interesting thing from this result. And this is about the relation between the tradability and the recapitulation score. So generally, in general, we observe some high recapitulation scores in the non-tradable industries like education and retail trade and construction. And we observe a lower recapitulation score in the tradable industries like information and the finance and administration. And then we think this kind of tradability is very is closely related to the recapitulation. Yeah. So the reason is that if the industry is not tradable, then its product or services cannot be exchanged between the areas. So in this case, if the population size changes in an area, then the employment of this industry should be changed along with the population change to satisfy the demand in the area. But if the industry is tradable, then its product for services can be imported from the other regions. So in this case, if even if the population size of a city changes, the employment of industry in that region doesn't need to be changed along with the population changes. So that's the reason why the tradability is related to the recapitulation of industries. And there is one more another interesting from this result, and this is about the characteristics of the high-tech industries. So high-tech industries are mostly superlinear and tradable. So they are mostly concentrated in the large cities, and their product or services can be traded between areas. So in this case, even if a small city grows, the employment in the high-tech industry doesn't need to grow along with this population growth. So we think that this kind of characteristics of the high-tech industries could intensify the economic polarization between small and large cities. And this is the last result of this paper. So we validated the recapitulation for the different city groups. So for the city groups of different sizes, so we measure the recapitulation score for the city groups and then averaged it over the industries. So the left figure shows the recapitulation score for different city groups. And we observe relatively high recapitulation score over the city groups of different population sizes, and except for a few very small groups. So this result shows that combined with the our former result about the industry recapitulation, the recapitulation is prevalent in most industries and cities. So yeah, this is a summary. So in summary, we show that the scaling properties divide urban economies at the population of 1.2 million. And then we derived an analytic model that connects the concept of RCA and the scaling relation. And this model estimates this point of transition at the 1.2 million population. And the urban scaling relation express the longitudinal trajectories of the cities in most of industries. And there are a few implications from that. First, combining the result of this, the different economic structures by population and the recapitulation, we can conclude that cities transition from the mature small city economy to innovate large cities economy as they grow. And one interesting from this observation is that the tradeability controls the degree of the recapitulation, and the characteristics of the high-tech industries could intensify the economic polarization between the cities. Yeah, this is the end of my talk. Yeah, thank you for attention.
Thank you so much, Inho, for this fascinating talk. And if I could say so myself, maybe we should have some time, maybe the next 10-15 minutes to ask questions and have a discussion, and then we'll close the meeting, or the seminar. So questions. I think if somebody, I don't know if we're using like a seminar specific setting, but perhaps we could just use if somebody wants to ask a question, if their video is not on, so they cannot raise their hand, maybe just say something in the chat, or perhaps just talk. And then I think there aren't many people, so we're not going to talk over each other.
Hi, Inho. This is Alex. Thanks a lot. This is really good. It's not the first time I've seen the work, but I get something more out of it each time. Just a quick question about. Could you just say a word about like any robustness checks that you did? I think the data is something like 16 years by, I think you said about 12 industry groupings, and then by the number of cities, which is like something like 300 in the US, roughly, I guess. So it's not like big data, but it's not tiny. I wonder if you could just say something about any robustness checks or like these sort of certainty estimation that you did.
First of all, actually we tried this main result is about the time difference between 16 years, like from the 1998 to 2013, and we also tried to measure the this kind of the recapitulation pattern for the like a 1 year difference set, and we also find the similar result from this the evaluation, but this degree of recapitulation is a bit lower than we observed from the change of the 16 years. So yeah, we mainly presented this result for our finding, and yeah, and also this recapitulation score is based on the measurement of the longitudinal scaling relation, and this the value is measured by the regression analysis on the linearized equation, and then there's some we can get some confidence interval for the regression analysis, and yeah, we measured that in general the value of the longitudinal scaling effect have good confidence interval for from the analysis. Yeah, so that's my answer for the robustness.
Cool, thank you.
Inho, I have a question.
Hi.
Sure. First, congratulations for the paper and the presentation.
Thank you.
Very nice. My question is related to this 1.2 million division that you find. This result is a division that reflects the year of 2013, right? So
actually, this division is based on the average of the time scope, but the scale relation during in this time scope doesn't change much. So I think it doesn't have much the temporal variations by the observation time. Yeah.
Okay, so that's why would be my second question, is how that point, how this number changes in time, and if there is any relationship, and for example, if this pandemics would change this number, and so you don't see too much difference, right? If you, for example, consider a different period of time, or for example, sliding windows, I don't know, just to see how these number evolve.
Oh yeah, I have two answers. Yeah, first one is that this 1.2 million population value is it depends on the population distribution, and also the distribution of the scaling exponent. So if one of these two may change, then the value of the transition could change. So of course, we observe the different values for different country. So this 1.2 million population is only for the United States, and I don't think there was a big change between in our time scope, but maybe this just is my guess, but this pandemic situation had a very great impact on the U.S. employment. So maybe the scaling relation could be changed during the pandemic. So in this case, this 1.2 million population, the transition point could be changed. Yeah. So I think it would be interesting to observe this kind of changes from the data.
If I could add a point to this, I mean, the question, Leonardo's question is good, and it, I think, goes to the crux of what actually causes this scaling relation. And I think we don't really know. I mean, the best theory that I know of is something that Manuel actually worked on, which is that the density, that as you scale size, the density of interconnections increases. But what drives this? Is it face-to-face interaction? Does this change because of information technology, which facilitates face-to-face interaction even at a distance? I think these are all open questions, and maybe the time scale, the time span that studied doesn't really capture this. Although there are interesting theories, people 18 years ago, the internet was not really a big part of business. So I just don't know whether the time scope is sufficient. But I imagine that if communication density is the driver, then technology that alters communication should play a role.
Very nice. Yeah. Thanks for the explanations.
Hi, Inho. This is Jason. Thank you all so very much for the fascinating talk.
Thank you.
Just taking it up from where Leonardo and Ian left it, could you just imagine if there was an ambitious project that would, say, digitize the related data of the last, I don't know, 4 or 5 centuries, say, in which are scattered in sources and would give you related data in terms of employment, or how these also move in, because I suppose they wouldn't be spatially necessarily located, right? Cities grow and fall, and they might not be in the same place. They might not have been in the same place 300 years ago. But do you think we would then have had an idea of a temporal change with this scaling number, so that probably the population of the Earth at the time was different, so we wouldn't have necessarily 1.2 million. I would expect that this is a historical transition, right? What Iyad was saying, that we see, if we see the big picture, right? It's a transition from agrarian societies to industrial, then to a society of services, and so on and so forth. So could you just, my question is, could you just have, would you imagine if it would be possible developing such a model of sparse data, which would be probably the case, dependent on historical data, like real historical sources, I mean?
Yeah, a great question. Yeah, as I said, this 1.2 population is depends on the distribution of the population size, and also it depends on the distribution of the scaling exponent. So if we go back to like 400 to 500 years old, then the population, the distribution of the population size would be different. It's like yeah, it's not only about the scaling exponent. So the size of the minimum city and the size of the largest city will be much more smaller than the current the cities. So this 1.2 million population size will be more smaller, yeah, population size at this moment. And the other one, the scaling exponent, the distribution of the scaling exponent. So in that period, of course the definition of the industry is different. So maybe in this period, the manufacturing could be the most the high tech the industries, yeah, like the IT or the professional services is have the highest scaling exponent in these days. So we should consider the industry sectors at this moment, and then maybe the agriculture or mining could have a more higher, more like a prestige in that period. So I think the scaling relations will be different from from now, but maybe the distribution of the scaling exponent could be the same. So even if the type of industry is different, because in any time there was some industry that have like a lower prestige, and the industry that needs more high tech or yeah, some brand new technology. So I think this kind of the scaling structure could be like the consistent in time, but it's very difficult. I think it's very difficult to define this kind of the industry sectors. But yeah, so in this point of view, so if we measure this kind of the transition point, then it will be like yeah, depending on the population distribution. So in our study, this 1.2 million population correspond to the the 50th largest city. So we have total 350 cities. It's like the 1/7. So maybe if there was like 100 cities in the like 400 years or 500 years in the United States, then this transition point could be at the like at the city, yeah, of the like a top, yeah, 1/7 city, yeah, at this moment. Yeah, that's just, yeah, my guess. So
yeah, great. Thank you for the insight. Great work.
Do we have any other questions? Okay, if there are no other questions, I want to thank everyone for attending, and thank Inho especially for presenting and dealing with all of these interesting questions. I hope that this will generate more discussion going forward. Thank you all for attending, and we will hopefully follow up, and you'll hear soon about the next seminar. And by the way, if anybody else would like to present some of the previous work or ongoing work as a seminar, please also do propose. We're always looking for local speakers from CHM as well as external ones. Okay, take care, everyone. Talk to you soon. We'll see you probably at the business meeting next week.
thank you for attention.
Bye-bye.